In this video, we will learn how to define a convolution neural network and then train it using a dataset. For that, we will use a Python-based deep learning framework called PyTorch, and we will run all the training process on a cloud-based GPU service which is called Google Colab. So let's begin. To start with, the very first thing we need to do is go to this website called pytorch.org and then move ahead to a tutorials tab, and on the left side you will see learning PyTorch, and if you click on this you can see a deep learning with PyTorch. Here there are a lot of learning material, and this video is about introducing PyTorch, so you can have a look at this. So for this for our session we will have a look at this post. So if you click on this you will see three tabs on the top. So we will select the run in Google Colab. So this will open a Google Colab tab, and if you have not logged in to your Google account, you will have to first log into it, and this page will open. So this is the interface for Google Colab, and the very first thing we need to do is define the GPU. So to do that, you have to go to runtime and click on change runtime type. So by default it is set to none, so we are not using any GPU by default. So to use a GPU we have to click on this and select GPU. So the interface is like this. So the one with the play button is a code cell which we can run, and the other tabs are the command tabs. So to run a code cell you have to press shift enter, and then this will run this code cell. The first cell always takes some time. So this has run now, and to see how much GPU resource we have got, you can click on this plus code button, which will create a new code cell, and in that you can type NVIDIA SMI, and if you press shift enter you can see the details of the GPU which has been allotted to us. So it has roughly 12 GB memory space, and it is of CUDA version 11.2, and you can see also the type of GPU device which has been allotted to us. So this is okay, and then we move to next cell. So this cell defines imports all the relevant PyTorch libraries, and to run it we have to press shift and enter. Yeah, so before that let's see what are the steps which are necessary to train an image classifier. So the very first thing, these steps are described here. So the very first thing is that you have to load the data first, and then you have to define a convolution neural network architecture, and then you have to define a loss function and a optimizer, and then once all these things are in place we can train our network. And this fourth step is a very lengthy process, and it takes some time to train the network, and then once it is trained we can test it on the test data. So this is the normal pipeline. So let's follow this one by one. So as we mentioned, we have to load the data first. So the first thing is we have to normalize the data so that it is in the range of -1 to 1. This is necessary to uh, for better convergence of these networks, of this CNN networks. And the next is batch size. We can set higher batch size since we are using a GPU. Let's make it 1024. So the batch size is basically the number of images which will be processed at once. So we will be giving 1024 images at once to a CNN. The next is the train set and train loader. and we have to similarly define the test set and the test loader. So PyTorch has done all the work for us. So by just calling this line, it returns a train set, which basically is a list containing all the items of the train set images. And in fact, if you run this and you print length of train set, so you can see that there are total 50,000 train set images, and similarly for test set we can see that there are 10,000 test set images. So the PyTorch has done all the work, and if you want to use custom data, we have to write this function by ourselves. So this we will see in the intermediate sessions. So for now, we can go ahead with this. So once we have the train set, the next step is the data loader. So data loader is basically uh, sections out this entire train set into batches. So the data set consists of 50,000 images, and then each batch will contain a total of 1024 images. So this is the purpose of train loader. The data loader actually divides the entire data set into a number of images, which is defined by the batch size. So this is basically a iterator, and if you call this loop through this iterator, every time you will get a total of 1024 images. So this is the concept of data loader and the batch size. Assuming this is clear, we can go ahead. Now you can see that just a cross check. So to print the length of train set, it is 50,000, and then if you want to see how many batches this train loader will compute, is as follows. So 50,000 divided by 1024. So each batch consists of 1024 images, and there are total of 50,000 images. So the number of batches which will be created is 49. So the total of 49 batches are required to process the entire data set. So this is something to note out. And then if this is clear, let's move to plotting some of the images. So to plot some of the images, we have to denormalize the normalization which we have done, and this is being done here. And then you iterate the data loader, and you get a set of images and labels. So now this will be a total of 1024 images. So for this for plotting purpose, let's only plot 4 images. So to 4, and then total of 4. So let's plot 4 images and the corresponding labels. So you can see this is a bird, this is a dog, and so on. Now that the dataset is in place, the next task is to define a convolution neural network. So this step basically defines the this cell basically defines the convolution neural network. So we know that CNN is a stack of convolution layers. So here there are 2 convolution layers, and followed by a fully connected layer. So let's quickly see what are these numbers. So if you want to learn about this, you can just you can just place the cursor there on top, and you can see the definition. So the first argument is in channel, the number of input channels. Since this is a color image, we have 3 channels, which is RGB. The next argument is out channel, where basically the number of it is basically the number of output feature maps, and the third is the kernel size. So here we are using a 5 cross 5 kernel, and we are using 6 such 5 cross 5 kernel. So uh, so since there are 6 kernels, we get 6 output maps. So this is the concept. and then we have a max polling layer. So this is a basically a 2 cross 2 window size, and we are taking the maximum of the 2 cross 2 window. And then these are the linear layers, and to know more you can just place the cursor there and it will show the definition. So this is the forward pass. So forward function defines how the input image will be passed through the network. So first it will pass through a con1 layer, and then a ReLU function will be applied to it, and then the pooling operation will be applied, and this process repeats. So this is how it is done. And since we are using a GPU, we have to load this model on a GPU. So to do that, we have to do this. So device is equal to torch.device. We will set to CUDA if torch.CUDA dot is available. Else we set to CPU, and then we push this network to the device. So just a cross check, if you print device, you'll see it is CUDA. So we are in the right track. Now that a network is defined and a dataset is defined, the next thing is the loss function and optimizer. So the concept of loss function and optimizer is as follows. So the network at first is a very dummy network. So when you pass the input, it will give wrong predictions. So when you match the predictions with the ground truth, there will be a loss. So this loss is unwanted loss, and the network should try to minimize this loss. So this loss is minimized using an optimizer. So how it does is it tries to compute the gradients of loss with respect to each and every parameter, and depending on this gradient it tries to update the weights so that the loss becomes minimum in the next iteration, and this process is repeated. So this is how we define the loss function and the optimizer. So here we have used cross entropy loss, and we have used SGD, which is stochastic gradient descent optimizer. To know more about this, I will put some links in the description which you can access. Now once this is set, we are all ready to go. The next is the training loop, where we will try to train the network. Since we are running on the GPU, we can set the number of epochs as 100. Yeah, so what is an epoch? So we discussed that we have the entire data set, and we have a data loader which tries to give every time when you call the data loader, it gives a batch size number of images. So now we have seen that there will be 49 such batches, and when we process all these 49 batches, we say one epoch is completed. So one epoch is basically the phase where we process all the data in the dataset. So we do this process multiple times. So we run the training loop multiple times. So this is that number. So we will run for 100 epochs, and we have to do one more step here. Since we have put the network on GPU, we have to also put the inputs and the ground truth on the GPU. So to do that, we have to say inputs equal to inputs dot to device. Similarly, labels equal to labels dot to device. So now we are all set, and so it goes this way. The training loop goes this way. Once we have the data, we first zero out all the zero out the gradients present in the optimizer, and then we pass the input, and we pass the outputs of the network along with the ground truth labels to a criterion function, which is the loss function. So this computes the error, and we try to backpropagate this error. So loss.backward basically computes all the gradients of the error with respect to each and every parameter using a chain rule, and the optimizer then uses these gradients to update the weights, parameter weights, model parameter weights. So this is the pipeline, and since we have a total of 49 batches as we have seen on top, just a recap. So we have seen that we have a total of 49 batches since we are using a batch size of 1024. So what we have to do here is print every 30th mini batch. So small change has to be done here, and then 30. So this is just a cross check just to see if the network is actually getting learned or not. So this will print the loss in the every 30 mini batch, and once we are set, can run this. So this is the most time consuming process. Let's begin. So let's see if the model is learning or not. So you can see that in the first 30th iterations our loss is 2.3. So every time a mini batch is processed, we call it one iteration. So these terms are sometimes confusing, so you can keep a note of this. So we can see that the model is learning very slowly. So let's stop for some time and increase the learning rate so that it can learn faster. So this learning rate is basically how fast the updates in the parameters will happen. So since we have reduced the learning rate now, the weights will be updated faster, and this will speed up the learning process. So let's just see. So in the first 30 iteration, it is 2.3. It's 2.297. So it is learning a little faster. And to see the GPU usage, you can click on manage sessions, and you can see that GPU is used. So if this is 0, then something is wrong, and you have to check why it is not happening, why it is not running on GPU. So this is how we can verify, and we can see that the network is learning now. And so this is a time consuming process, so let me pause the video and come back once it is trained. Okay, so the training process is completed, and we can see that the loss has kept on reducing, and after 100th epoch it is 0.5. Now let's save our network and test it on the test data. So to do it, we have to iterate the test loader, and you can see since our batch size is huge, we can just plot 4 images. So total of 4, and you can see the test images. Now this is the ground truth. So now let's see what the network gives the predictions. So to do that, we first define the network and load the weights from the saved model. So first a network is defined, and we load the weights from a saved model. It says all keys matched successfully. Now we pass the images to the model and obtain outputs. And so output is basically a probability distribution across all the 10 classes. And to find the predicted class, you have to find at which location there is a maximum. So we use torch.max. For example, if it is not clear, if you print outputs.shape, you can see that there is for each image there are total of 10 values. So this is a probability distribution, and we have to take torch.max to find the prediction. If we see, the predictions are as follows: cat, car, sheep, and sheep. Let's compare it with ground truth. So cat, car, sheep, and planes. So we can see two of the predictions are wrong for these four images. So now let's see how the network has performed on the entire dataset. So it loops through all the images in the test loader, passes the images to the network, obtains the output and the predictions, and see uh, how many predictions are correctly labeled, and this gives the total accuracy. So the total accuracy on a total of 10,000 images is 61%. So there are more than 6,000 images which are correctly classified. So this is a not bad accuracy. In fact, this accuracy is obtained using a CNN is much more than all the handcrafted feature extraction approaches. And since this is a very difficult data set, it has you can see the images which are very complex with complex background. So this is a pretty decent accuracy on this data set. And as we move ahead in this series, we will learn to build better model architectures, and using that we will get even better accuracies. And so this cell is about analyzing on which class it is performing good or bad. So we can see that on most of the classes the accuracy is more than 50%, but for cat it is less than 50%. So this we can analyze, and when we build a better model architectures, these accuracies will improve. So that's all for this